Alhamdulillahi Rabbil Alameen wassalatu wassalamu ala Sayyidina Muhammad. Amma ba'd. Have a think about the famous painting called Mona Lisa. It's known throughout the world. It's one of the most, if not the most expensive painting in the world. Now let's approach our understanding of this painting of the Mona Lisa through using the scientific method. What conclusions are we going to come to using the scientific method? Well, as we mentioned, the scientific method is really good at understanding the observable, the testable, and the repeatable. So we can work out maybe what type of colours were used, what was the composition of the paint, what was the composition of the material that was used for the canvas, or even the frame. These are things within our direct observation, within the experimental field. But we have to ask ourselves the question, what's outside of the scientific method? What's outside of the experimental field and therefore the empirical approach? The obvious question is the painter. Science, although incredibly useful when it comes to those things which are directly sensible and testable and repeatable, cannot be used to determine matters which are outside of its scope and the directly observable and the directly sensible. Does that mean that because we can't prove it through a scientific approach, that the painter does not exist? Well, obviously the painter exists. In fact, we know who that painter is of the Mona Lisa. It's Leonardo da Vinci, at the beginning of the 16th century, in fact. All of this we know with a high degree of certainty, i.e. who the person was and roughly or quite confidently when it was, which period of time, at least which century it took place. And all of these answers that we can understand with a high degree of certainty comes outside of experimentation and the scientific method. Similarly, when we look at the painting, and maybe some people might say it's beautiful, exquisite, other people might say, oh, it's ugly. What is our aesthetic reception for this particular painting? Does it move us to emotion? And what type of emotion? These questions again are outside of science. Yet it doesn't mean that we don't have emotions, that we don't have an appreciation of what we think is beautiful or what we think is ugly. And that's, and some people might say, well, maybe we can through science. Maybe we can, look at a brain scan and look at regions of the brain that are being highlighted. But just simply highlighting regions of the brain doesn't say what type of emotions, or more importantly, the experience of that emotions, because the experience of emotions is very personal to each individual. And this comes to another question, which regards to consciousness. How do you know that I am a conscious being? Do you know it by simply studying the science of my brain activity? If you haven't studied my brain activity, does that mean that you are unsure whether I'm a conscious being or not? In fact, some people might say, okay, not only can we do brain scans, but also we can look at action potentials of neurons. These are electrical signals that travel across the neurons of the brain. Or that we can, understand and test what type of chemicals are being released at the presynaptic neuron, known as neurotransmitters. Yet none of this explains what it means to be me, what it means to experience something, whether that's a painting, whether that's poetry or something else. What it feels to be consciously aware. Many scientists and philosophers are aware of this problem of consciousness, even just how to define what the term consciousness is from a purely materialistic explanation. This is why they call it the hard problem of science, consciousness being the hard problem of science. And some might say, well, in the future, we will work it out. We will be able to define through the use of empiricism and science that consciousness exists. And that we'll be able to determine that a person is conscious or not, in terms of and what it means to be conscious for that individual. But even if they say in the future we'll be able to determine this, it doesn't deny the fact that we can be sure to now and understand and comprehend now that a person is conscious or not. Hopefully you're still conscious watching these videos. So Whether we look at the painting example, whether we look at the consciousness example, these are two relatively simple examples that demonstrated the limited applicability of science. That is not to say that science isn't a useful tool. And like I said, it's been very useful. It's helped us develop medicine, surgery, space travel, telecommunications. But rather, and also it was utilized by the Muslims of the past as well, famous Muslim scientists, including people who say that Ibn al-Haytham, the famous Muslim scientist of the past, helped create in part, or helped formulate in part, the scientific method. But the problem now is not the fact that people are using science, it's the fact that they approach all questions with the use of science and claim that anything that's not scientific and empirically verifiable is therefore unprovable, untestable, or doesn't exist. And this is what we call scientism. In one definition, it's described as totalizing the view of science, as if it were capable of describing all reality and knowledge, or as if it were the only true way to acquire knowledge about reality and the nature of things. So statements like, science is the only way to know truth, or science will answer all questions, these statements are actually non-scientific statements. I want you to follow this point. When a person turns around and says, all answers or all ideas are derived from science, or science will answer all questions, is that a testifiable scientific statement? So are they using science to justify science? If they are, then it's a circular argument, what we term tautology. So these are non-scientific statements. They are better known as metaphysical statements, statements that are accepted or assumed to be true. So in essence, when a person says that only science can answer all questions, that's actually a self-refuting argument. And that's the first problem with this approach, with scientism. The second problem, as we've described in the examples above, is that we know certain things and are very sure about these things, but without the scientific method. Like, for example, if I was to ask the question, do you believe that your great, 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 great grandmother existed? Everybody will say yes, irrespective of whether we knew who that great, 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 great grandmother was. Irrespective if we had a number of people claiming to be, or potentially could be, our great, 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 great grandmother. Irrespective of whether we even, have a grave to test the DNA in order to determine this. So irrespective of any scientific arguments to justify this great, 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 great grandmother existence, we know we had one. So again, it proves this point, which is that there are certain things we are 100% sure about without the use of science. Furthermore, the scientific method in the vast majority of cases leads to what we term inductive conclusions. And I think we need to explain what induction means here. But just before I do, I believe it's also important to explain and gain a bit more crystal understanding of what exactly we mean by the scientific method. Now, if we cast our minds back to when we were at school, or maybe those people who do science at university, and we were asked to write up a scientific experiment, then there was a very specific way in how this scientific experiment had to be written up. And this is called the scientific method. And that is, you would have an aim, you would have a method, you would have results, and you'd also have a conclusion. So what was the aim? The aim identified the purpose of the experiment, what you wanted to find out. The aim also may have included a hypothesis, what you may see. And also the aim defined for us what variables we were looking to test. The method. The method was explaining how we isolated the various variables and what conditions and causes we subjected them to, or we observed them in what types of conditions. The results was the data we obtained from this experiment, or these observations. And the conclusion was an understanding of what that relationship was between our observation and the results. and whether this confirmed our hypothesis or denied our hypothesis. Now it sounds a bit complicated, but let me break it down even further. Imagine if we were to do an experiment and talk about maybe the boiling point of water. Very simple experiment. We all know what the boiling point of water is, but let's say we wanted to prove this point. So we would define, in our aim that we want to look at the boiling point of water. We would define in our method the method of achieving this. So we'd say we'll take pure water at room conditions at 1 atmosphere. We will subject it to heat using maybe a Bunsen burner, and we'll record the temperature with a thermometer. And then we would record, and we would do this experiment where we heated the water up and record that it boiled at 100 degrees Celsius. We would then test it and repeat it. So we would repeat this process in order to get maybe further confirmations. That could have been an incorrect or an abnormal reading. So we wanted to test it. So we test it again, and maybe after the 5th time we find that water boils at 100 degrees Celsius, we can say, okay, in our conclusions, we can say that when we subjected water to heat, we found that it boiled at 100 degrees Celsius. This is our conclusion. Now, that conclusion on the issue of water is what we call an induced conclusion, or inductive process, or inductive conclusion. So let's explain what do we mean by induction, and the opposite of that, or the other aspect of that, is called deduction. So induction is understood where you go from the particular to the generalized. Give you a very famous example that's always found in all different books where it talks about induction, is the example of swans. What color are swans? So maybe you go out and you'll see 1 swan, 2 swans, 3 swans, 999 swans, and all of them, 999, were all white. So you took particular observations, and then you said as your conclusion, all swans are white. So you're going from the particular to the generalized. But what about the 1000th swan? Yeah, maybe you come across later on another swan, 1000th swan, and you find it's black. So what you find with the problem with induction is that induction, when you go from particular to the general, there may be some evidence that you are unaware of. There may be some observation that you've not come across, which therefore defeats or undermines the whole of your conclusion. So scientific theories, or even when people turn around and talk about scientific facts, are not really facts per se. They're not 100%, but rather they are induced. They are things which are, based upon the maybe true or valid based upon the current data set that you have. Deduction works the other way around. Deduction is when you go from the general and you come to a particular conclusion. So again, the famous example is all men are mortal. General statement. Socrates is a man. Therefore, Socrates is mortal. So you've gone from the general, all men are mortal, to a specific conclusion, Socrates is therefore mortal. So this was what we call a deduction. So with regards to the issue of the water boiling, how do we know that the water boils at 100 degrees Celsius as a generalized statement based upon 4 observations? Even if we, say 1,000 observations or 1,000,000 observations, how do we know the 1,000,001th time when we observe water, it actually boils different? That's because whenever we say a statement like all water boils at 100 degrees Celsius, what we're saying is that all water that existed, that does exist, and that will exist boils at 100 degrees Celsius. But we can't make that statement. And the reason why we can't make that statement is because we've not sensed all water that has existed, that does exist, and that will exist in the future. Therefore, we've generalized this, and that's where one of the key problems with regards to science is that science cannot be or cannot lead to certainty, i.e. scientific theories, unless you've totally observed the reality of the particular subject matter at hand. So even things like the theory of gravity, the laws of nature known as, like, for example, the laws of thermodynamics, they're termed laws. the idea would be is that they're set in stone, they cannot change. All of these things are induced. They're true or they're valid, but based upon a limited set of data, even if it's a million evidences or a billion evidences. So science can never lead to 100%. And as a side point in regards to evolution, it's the same thing. You find people like, atheists, Richard Dawkins, others, who say, yes, evolution is an absolute fact. It's a scientific fact. But really, if you identify what science is and the philosophy behind science, you realize that science doesn't deal in facts. And this isn't something that, isn't aware from certain people, either philosophers of science. People like Bertrand Russell, Karl Popper, and also the famous 18th century empiricist and philosopher known as David Hume, they all understood the inductive or the indefinite nature of science. Karl Popper, in fact, he was an empiricist, and he came and he looked at this idea of science not being able to establish truths, and he started to talk about how actually science should be in the not the business of dealing with truths, but rather the business of falsifying statements. And that's where he came up with the idea of falsificationism or the falsifiability. He said that science, due to its inductive nature, can never make true generalized statements. What we therefore can't say is that water boils at 100 degrees Celsius. But what we, according to Karl Popper, can say is that water boiling at 100 degrees Celsius is a valid proposition, a valid statement that has not yet been falsified. So this is his position, that a statement can't be said to be true. It can only be said to be valid until evidence has falsified it. And if there's no evidence that's falsified it, it remains a valid statement. So we can see that actually when we look at and understand science, and in terms of the evidences and the conclusions, that they're not 100%. But there's more to it than this. The scientific method is built on specific axioms. Axioms here means, assumptions that we have to accept. One of those axioms that science is built upon is the idea that causality exists. So for example, when I want to work out the boiling point of water, what do? I assume that heat will cause the boiling point. So even prior to engaging in the scientific experiment, I'm going to place a flame or fire or heat underneath the water. The cause would be the heat and the effect would be the boiling point. But what was really interesting to note, and this is what David Hume himself noted, is that causality cannot be proven. It has to be assumed. See, when you put water or heat beneath a water, you notice an effect. You notice something resulting. So you have two events, heat and boiling of water. But our mind makes the connection of the causality or the relationship between the heat and the water. Otherwise, it's just an observation. David Hume, he gave an example of this, of a billiard table. Maybe modern day example would be a pool table. And he said, imagine if you had a person who had never seen a pool table in his life. And he sees the white ball traveling towards the black ball. What would he expect? What's his expectation? Now, because he's never seen this event occur, he doesn't know what to expect. Could be that the white ball bounces off the black ball. It could be that the white ball, smashes through the black ball. It could be that the white ball passes directly through the black ball. Or it could be that the black ball bounces off and moves in another direction. There's a number of potential possibilities. So David Hume, in the billiard ball example, he said, well, he sees this event and he sees the black ball move after being hit by the white ball. So he does it a second time. Now the question becomes, what would he expect when he repeats this the second time, even with all the variables the same? Our intuitive understanding would be that the black ball will move, meaning that the second event will resemble and follow the past event. David Hume said that's an assumption. The assumption being that future events follow the same pattern as past experiences, because the same number of potential possibilities still exist. The white ball could bounce off the black ball. The black ball could be disintegrated. The white ball could go straight through the black ball, or the black ball could move. The same number of potential possibilities could still occur. So he said, David Hume, using this example, he's explaining this point, which is that you can't know for certain that causality exists, and you can't know that definitely future events will resemble past experiences. But this is exactly how science works. Science has to work by saying future events will resemble past experiences. Otherwise, there would be no science. And causality has to be assumed. Otherwise, we would not do any experiments. And maybe just to give you another quick example of this. They discovered stars that were orbiting in galaxies, and they orbited around a central mass known as a super black hole or supermassive black hole. And they noticed that the stars on the very edges of these galaxies that were orbiting were going too fast. They were going the same speed as stars that were orbiting closer to the core. And so they said, well, hold on. According to our theories and the law of gravity, that shouldn't be the case. If you swing a ball on a string too fast, what's going to happen? The string is going to break and the ball's going to fly out into the air. So they're saying this is what should happen with regards to stars that are orbiting on the edges. They should be slower in order to maintain its orbit, but they're not. They're fast. And so they had two options. Either change the theory of gravity, so change how we understand how gravity works, or the second option was to say there must be something causing gravity to exist in order to allow this to exist. And what they said was, well, hold on, gravity we generally accept, it generally works even though it's inductive. So they changed, or they not changed, they developed a new idea that there is a new form of matter that exists within the universe, and they call this dark matter. And it's this dark matter that we cannot see, we cannot taste, we cannot touch, but is exerting effects upon the orbits of stars within galaxies. So this is just an example that shows how causality is necessary for science to work. Without causality, science doesn't work. So to quickly sum up, science, those who claim that science answers all questions, that's not even a statement that can be verifiable by science. 2, science leads to indefinite conclusions due to its inductive nature. So you can never be 100% sure, even with most well-established scientific theories. Thirdly, science has to assume certain axioms, like causality, like that the future events will follow past experiences, and that there are fixed patterns within nature. That causality cannot be proven, but assumed within the scientific method itself. And finally, that even if something doesn't fit within the scientific method, that doesn't mean that the subject matter cannot be proven. And this is summed up by Imam Ghazali in his Al-Mustasfa, where he refutes the empiricists of his day. And I'll just summarize what Imam Ghazali said in his book Al-Mustasfa. He explained that you can't just simply say that the only truths we know is developed by what we experience. He said there are other truths. For example, that we know 1,000 is greater than 1. Yeah? These are known as synthetic propositions in mathematics, which are determined through a deductive process. He said we know that Baghdad exists even if we've never entered Baghdad, the city of Baghdad. Yeah, that China exists even though we've never been there. That historical events occurred, like for example, maybe we could say World War II we know existed even though I didn't live there, because there is also another form of knowledge known as historical narratives. Yeah, historical narratives can establish that certain things exist, or narrations that China exists or that Baghdad exists. And so Imam Ghazali explained that there are 3 ways to know. One is through experience, so we don't deny that. We can come to certain knowledge through experience. Second is that we can come to certain types of knowledge through historical narrations. And thirdly, we can come to certain types of knowledge through deductive arguments or synthetic propositions like in mathematics. This now allows us to move on to the subject of what is rational thinking and its components, and how we can use this method to approach the evidence for the belief in the Creator.